this computer. Perfect. Now it's seamless, right? Nobody has any idea. Okay, so last time I left off, I said, hey, look, there are two theorems here that we're going to prove. And the proofs of these are actually, they're going to be easier than uniform continuity, which we did last time. And uniform continuity, that proof was quite long, right? You remember I zoomed out and all the font ended up being very small because I had to zoom out so much. So we're going to prove these two theorems. These two theorems are very similar, but again, they're theorems about continuity, right? So we need that our function is continuous. And now in uniform continuity, there was actually this condition. We said they're implicit in the hypothesis is the fact that the domain is the closed and bounded interval AB, right? And you'll notice that both for the intermediate and extreme value theorems that I've stated here, we have that closed and bounded interval AB as the domain again, right? Now, there's a sense in which it's possible to strengthen both of these theorems so that we don't use the closed and bounded interval AB. But the problem is that the way that you strengthen them is different for both. There's something going on here topologically, and these are actually, in some sense, very different theorems. Basically, for the intermediate value theorem, the important thing that we're using is the fact that the interval is connected. So it's not broken into chunks. There's just like one big slab of interval, right, from A to B. And then the important thing for the extreme value theorem is that it's closed and it's bounded, right? And I think last time I gave examples of a couple of functions that if you didn't have a closed and bounded interval, it wouldn't work, right? So for the extreme value theorem, you actually are allowed to take that interval and break it into chunks, so long as those chunks are also closed and bounded. Okay, so that turns out to be true. And if you want, you can try and prove those more generalized results. But for our purposes, it's not a big deal. If you come take 257 with me or at St. George or wherever, then you'll see what I was talking about in those proofs, and you'll be able to recall back on today's lecture and be like, oh, okay, that's what he was talking about. So the first theorem that we're going to prove, well, yeah, let's do IVT first. Okay, so we're going to do IVT, the intermediate value theorem. And first thing I'm going to do is I'm going to prove a result that seems weaker, but is actually the same, right? So I'm going to just call this a proposition. So we're going to say if F is the map from AB to R is continuous, and F of A is less than 0, F of B is greater than 0, then there exists some point C in AB, really in this case, open AB, such that F of C is equal to 0, right? And hopefully we see like, yeah, that is a mean value, or sorry, an intermediate value theorem sort of thing. Now the intermediate value theorem said that any number between F of A and F of B could be realized. And this one just says, hey, listen, if FA is less than 0, F of B is greater than 0, then this particular number 0 can be realized by the function, right? So that feels weaker. It feels like if you, for example, if you knew the intermediate value theorem was true, that you could prove this theorem, no problem. But we're actually going to use this theorem to prove the intermediate value theorem, and therefore those theorems are actually equivalent, right? Okay, so we're going to prove this, and this is the one that's going to use sort of the weird technique. Once we have this, the proof of the intermediate value theorem is actually really easy. Oops. Oh, that was weird. So proof. Okay, let me just double check what it is we want to do here. I just don't want to make a mistake. Yes, okay. So what we're going to do is let's define, I'm going to call it n for like negative. So this is going to be the collection of all points in the interval AB where the function f is less than 0. All right, so it's the collection of all x in AB such that f of x is less than 0, right? So it's the points where f of x is negative. Okay, it is non-empty and it is bounded from above, right? So it's not empty because A is in here, right? We know f of A is less than 0. So it's non-empty since A is in N and bounded from above. By B, right? Because again, we said the elements in N have to be in the interval AB, so B is an upper bound, certainly. So therefore, by the completeness axiom, its supremum exists. And hopefully, again, you're having a little bit of deja vu. This is exactly what we had when we talked about uniform continuity, right? We defined a weird set like this, said it's not empty, bounded from above, took its supremum. So by the completeness axiom, what do I want to call it? I guess we'll call it C, kind of hinting as that this is the number that we want. C equals sup n exists. Okay. Now, when we were doing the uniform continuity result, we wanted to show that the supremum was actually B. Now, obviously, that doesn't make sense in this case. We know f of B is greater than 0, right? But I'm claiming that whatever the supremum is, it is in some sense, it's the biggest number for which f of C is less than 0. No, that doesn't quite make sense, right? Because then it would be less than 0. But yeah, you're taking the supremum of all the points where it's negative. And the argument is that if you think about that, if you even just draw any function that you want, and you think about the supremum of that, that will give you a point where C is equal to 0. There might be other ones, but we just need one, right? We just claim that there's one of them. So we're going to take the supremum of the set and show that it works. All right. And the way that we're going to do this is exactly by this like forcing argument. We're going to say, well, suppose it's not 0, and then show using continuity, well, then we could break the fact that the supremum, right, is the least upper bound. So for the sake of contradiction, or I guess we actually should say what we're trying to claim. So we claim that f of C is equal to 0, right? And then in the proof of this, so for a contradiction, suppose not. Okay, now technically we have two cases here. The cases are pretty similar though. The more likely thing is that if f of C is not 0, then it's probably negative. So if f of C is less than 0, then there exists, and now this was an exercise that I think I put up last time, or maybe it was in office hours on Monday, I don't remember, but we're continuous at C and we're less than 0, which means there's an entire interval on which we're less than 0. So here we're going to assume it's less than 0. Yeah, exactly. So it does have to be either greater than 0 or less than 0. We'll kind of do those as two separate cases, but we'll start with less than 0 here, right? So if f of C is less than 0, then since f is continuous, there exists a row greater than 0 such that f of x is less than 0 for all x in C minus row, C plus row. Okay. Now I don't remember when I stated this result. So if any of you are like confused as to how I was able to conclude this, you should say something now. You should be like, wait a second, why do we know that that's true? Right? Does everyone remember this? Should I maybe state it as a separate thing? Maybe. Right. Okay. So maybe let me state it as a result. I think it's one of the bonus questions. I don't think it's an assignment question. I think it's one of the bonus ones. But basically the result that we're going to use here, this is such an important result. You're going to use it all the time. If f is continuous, usually we state it for positive, but that doesn't matter, at the point C, and f of C, like I said, I'm going to state it for greater than 0, but it's the same thing. And you can see the theorem is basically exactly what I just wrote down above, right? So namely, a continuous function that's positive at a point actually has to be positive near that point as well, right? Because the function is continuous, it can't just instantly jump from being negative to being positive. It has to actually go through a series of positive numbers, right? And this is the proof. I think Sophia Maria asked about it, and it was something about visualizing, like turning the visualization into like mathematizing the picture, right? And then we drew the picture, and I said, see if you can prove it. It was there. Okay, perfect. Yeah. And when was that? Was that in office hours or was that on Tuesday? Okay, so that's why, right? So some people weren't there. So it is an extra assignment, and we did talk about it. We talked about it in office hours. So there is the theorem for you. Try and prove that. That is a great proof. We're going to use it a lot. So make sure that you can do that one. Okay. And here immediately now, we see what our contradiction is. Well, f of x is now less than 0 up to c plus rho, right? So that means that c plus rho is actually an upper bound now for, what do I want to say? Or here, let's take c plus rho over 2. So thus, let's just choose a concrete point. F of c plus rho over 2 is less than 0, which contradicts the fact that c is an upper bound. For n, right? Remember, n was the collection of points. Let me maybe just zoom out a bit. N is the collection of points where f is strictly negative. And we said that c is its supremum, right? Which means no number bigger than c can be less than 0. That's the less, that's what it means to be the supremum. It's the least upper bound. So the fact that we found now a number bigger than c, which made f negative, contradicts the fact that c was an upper bound, right? In particular, the supremum. So yeah, it can't be less than 0. Now, on the other side of things, we would also technically have to worry somehow whether f of c was bigger than 0. Right, so that's a different case. I'm going to do this one a little bit quicker. So I'm going to say by the same argument, if you're positive, if f of c is greater than 0, there's a whole interval on which you're positive. Right, did I zoom back in? I don't know. So there exists a rho greater than 0. Such that f of x is greater than 0 for all x in c minus rho, c plus rho, right? But then c minus rho over 2 is an upper bound, which is less than c. I guess I should say an upper bound for n. Which is less than c, right? Which again is a contradiction, right? It contradicts the fact that it's the least upper bound. Right, so that's also a contradiction. Right, and in total, what do we get then? Thus, f of c. It couldn't be less than 0. It couldn't be bigger than 0. So yeah, there's only one thing left that it could be. It's got to be equal to 0. Right? Okay. So with this result now, this is, I mean, half the time that you use the intermediate value theorem, this is actually the theorem that you're using anyway. But the intermediate value theorem does state something a little bit stronger, right? So this says if you know one point is negative, another point is positive, and your function is continuous in between, then it had to pass through 0. And again, that is intuitively obvious. Of course, it had to be, right? Here's the line y equals 0, or it's the x-axis. I know f of a is less than 0. F of b is bigger than 0. And I had to draw this without lifting my pen. Yeah, I have to pass through the line y equals 0. Why does a belong to n? So in the hypothesis, so we knew that f of a was less than 0. And n is the collection of points where f of x is less than 0. So yeah, a is in there, right? It is one of the points which makes f negative. So that's just how we know that it's right. Otherwise, if you started with a function that was everywhere above the x-axis, then this set would actually be empty and this proof wouldn't work. So it's critical that we actually knew that we started beneath 0, right, in order to make sure that the set was not empty. Okay. And I guess I started kind of drawing to the right or writing to the right there, but whatever. Okay, so now let's actually prove the IVT. And so basically what we're going to do is we're going to take whatever value you want, right? So you're going to give me some number between f of a and f of b, right? Let's call that number d or something. And all I'm going to do is I'm going to shift the whole function. I'm going to take the whole function. I'm just going to shift it down, right? So that d basically becomes a root of the function, and then I will apply this theorem, right? So I'm going to take the whole function, shift it down so that d would end up being a root, argue that f of a is less than 0, f of b is greater than 0, so there is a root, and then shift it back up, right? That's basically the idea there behind why the proof works. Okay. So yeah, did I even bother to write it down? I don't think I did, right? Because I was just like, you know how to prove this. Yeah. Okay, so let's define, or so let's say fix some point d in, maybe I should, let me go up very quickly so you remember what I'm actually proving. I just want to show you what the intermediate value theorem is, right? So these are our hypotheses. We've got the function mapping ab to r, it's continuous. We're assuming that f of a is less than f of b. Again, that's not critical. If you want to flip them, you can. And then we're going to say for every d in f of a, f of b, there is some c which maps to it, right? So for every value between f of a and f of b, there's something which maps to it, right? So I'm going to say fix some point d in f of a, f of b, and define a new function, same interval. And the way that we're going to do that, that's going to be f of x minus d, right? So like I said, we're just going to take d and we're going to shift the function down so that it becomes a root, right? So it suffices to find a c in AB such that g of c is equal to 0, right? Because in that case, then we would get f of c minus d is equal to 0, and so f of c is equal to d, right? Okay, so I need to show by the proposition that we just did, I need to show that g of a is less than 0 and g of b is bigger than 0, but that's immediately true, right? Because I've got f of a minus d. I guess I'm actually going to take this in the open interval here, just so I don't have to do cases. But if it's equal to f of a or f of b, obviously a and b work, right? Okay, so because d is in the interval f of a, f of b, then d is bigger than f of a, right? So this number is less than 0. And g of b, which is f of b minus d, well, f of b is bigger than d, right? So that's greater than 0. And so by the proposition, we're done. And so by the proposition, there exists some c in AB with g of c equals 0. And voila, finished. So even though that theorem seemed weaker, the reality is that you could actually use it to prove a better theorem, right? You could use it to prove that, yeah, you don't just need to be beneath 0 and above 0 to hit a root. You can actually hit any number between it just by kind of moving your function vertically up and down, right? So we've got our function, we've got some point d, we take the whole function, we just shift it down, and that's exactly how that works. Okay? Does that make sense? Does everyone see the picture when I say that? Right? Let me maybe just draw it, because this idea of kind of like shifting the function around is is useful because we're going to do it a couple times, especially when we get back to the mean value theorem, right? And let's say that this height here, let's say this is D. I guess maybe I should give myself a y-axis like so. All right, so that's D. And then what I'm going to do is I'm just going to shift everything down by D. Try and draw this the same, like that, right? Oh, I wonder if even I could somehow draw it. Maybe I can actually draw it in the same thing, and then that would be maybe even more illustrative. Okay, and let me maybe try and use a different color. So I'm gonna, I've got this height D here, and I'm gonna just drop everything by exactly that height. All right, so if the blue is y equals f of x, then the green is y equals f of x minus d. And now that point is a root, right? So that's how we use the theorem. We took the blue curve, we just shifted everything down so that it would end up being a root. Now I know that f of a is less than 0, f of b is greater than 0, and I've got the point C, which ends up working, right? So that's the idea there behind that actual proof of the IVT and why that works. No, so C is this point. C is the point in the domain, and then D is the value in the codomain, right? Like we want f of C to be equal to D. So they're playing different roles, right? D is the output, and then C is the input. So we're saying for every output D, I can find an input C such that f of C is equal to D. Does that make sense? Cool. Okay, now, normally I would do an example of one of these. I guess I should, but I want to get to the intermediate value theorem. So I'm probably going to do this one pretty quickly. And I think Sultan brought this up earlier in the year. I think it was you, Sultan, and if I've misnamed you, I'm sorry. That's kind of like, I think, very cool. This is one of my favorite examples of the intermediate value theorem. So suppose that we have a map from 0, 1 to 0, 1, and you know that map is continuous. The claim is that there is a fixed point of this function. Show that f has a fixed point. Okay, namely, so I'm going to tell you what a fixed point is. There exists some C in 0, 1. Such that f of C equals C, right? So that's what's special about it. It is a point such that it's the input and the output are the same in this case, right? F of C is equal to C. And the fixed point theorems are super important in mathematics. We use them all the time. All right, probably the most famous and probably the most useful is something called Brouwer's fixed point theorem. So if you want to look that up, you can. I'm not certain that you'll understand the statement of it, but it's probably the most important fixed point theorem ever. But basically what this theorem is saying is, okay, so the function's domain is 0, 1, but its codomain is also 0, 1. So basically the function, if you were to graph it, lives inside of this box here, right? And if you graph it, I guess I'm being inconsistent with my colors. So I'm going to draw it in green. But basically the idea is no matter what curve you draw, right, you can draw any function you want in this curve. At some point, it's going to have to pass through, oops, that is the wrong direction. At some point, it's going to have to pass through the line y equals x. Right? Because y equals x is precisely the point where the input and the output will be the same. So in that case, this is going to be our value here, right? This is going to be the fixed point, right? Wherever that curve intersects the line y equals x. So if I say draw whatever function you want inside of this box, at some point it's going to have to pass through this line. And it could do so minimally. It could do so only at the endpoint, 0 or 1. But that's fine. That still satisfies the solution. Right? So I'm going to say if f of 0 equals 0 or f of 1 equals 1, we're done. I don't actually know. I don't remember if that's important because I'm just kind of proving this on the fly. And now we're going to do our normal thing. Anytime, so the intermediate value theorem tells you when a function is equal to a point. If you want to say something about two functions being equal, the trick is just to subtract them, right? Always, that's the trick. So we're going to define g, also mapping 0, 1 to 0, 1 by g of x equals f of x minus x. This is continuous because the sum of continuous functions is continuous, right? So by subtracting x, I know f is continuous to begin with. The function, y, or the function whatever, k of x equals x is continuous. So sum of continuous functions is continuous. Is continuous. So g of x, so g is continuous. Okay, moreover, and I guess we didn't actually need the full inverse function or implicit function theorem for this, because g of a is going to be g of 0 is going to be just equal to f of a, right? F of a, what do I want to say here? What have I misdone? Oh yeah, which is obviously greater than 0. Oh yeah, because I flipped them, right? And g of 1 is, sorry, not f of a, f of 0, f of 1 minus 1, that's less than 0, right? Everyone agrees? F of a is greater than 0 because you know that the codomain is 0, 1. So it has to be, I guess, greater than or equal to 0. But if it's equal to 0, we're done. Right? And same thing with g of 1. So if, what do I want to say here? So again, neither of these, no, it actually has to be, no, these have to be strict because we already said f of 0 is not 0 and f of 1 is not 1, right? Because we've already assumed that that case is done. So these are strict. Thus, by the IVT, and if you want to say IVT, you can. There exists a C such that G of C is equal to 0, but that's the same thing as f of C minus C equals 0, or f of C equals C, right? And so we're done. So I did need, right? I did need to say, well, if f of 0 is 0 and f of 1 is 1, then we're done. So, I mean, I guess I didn't say it explicitly. Assume that that's not true, right? Assume that f of 0 is not 0 and f of 1 is not 1. I guess it might have been a little bit nicer if I wrote x minus f of x, because then g of 0 would have been less than 0 and g of 1 would have been greater than 0. I mean, obviously it doesn't matter. If you know it, you can just flip it, right? And everyone's okay with that too. Like in the proposition that we proved before the inverse function theorem, I said f of a had to be less than 0 and f of b had to be greater than 0. Now, if I asked you to prove the opposite, like that the theorem is still true when f of a is positive and f of b is negative, how would you prove it? Out of curiosity. Would you just redo the proof? But now with f of a being positive and f of b being negative. So what I mean is like up here. So in this proof, suppose that I flip these, right, up here. So suppose that I said f of a was positive and f of b was negative. Would you just repeat the proof, or what would you do? Does anyone have a better way? Close, very, very, very close. Right, exactly. And so don't do the proof for negative f. And Jinjin, same sort of idea. Okay, so what you want to do is you want to do like say, okay, consider the function negative f. Now that will actually flip it so that negative f of a is now less than 0, negative f of b is greater than 0. Now apply the previous proposition, which you've already proven, so don't prove it again. Apply the previous proposition, so you know that there's a root, so negative f of c is equal to 0, but you don't care about the negative side, right? Because if negative f of c is equal to 0, then f of c is equal to 0. Does that make sense? So Rui, yours won't work because then that ends up pushing both of those two numbers, f of a and f of b, to being above 0, and then we can't guarantee the existence of a root, right? So yeah, you use negative f of x. And so Jinjin, you almost had the right idea. You don't want the negative x to be on the inside. I don't think that'll work because all that does is kind of flip your interval over to being to the left. And our issue is that we wanted to take our 2 points and do this, right? So we didn't want to do this. We wanted to do this sort of thing. So you translated kind of horizontally instead of vertically. You flipped horizontally instead of vertically, right? Does that make sense? Try it, okay? That should be a one-line proof. So I think you should all try and prove it where you flip them and just make sure that you're kind of okay with it. Right, and then you understand why I only prove one direction. G of 0 can't be 0 because I've already, so basically up here, I'm saying if f of 0, so at the very top of the screen, if f of 0 equals 0 or f of 1 equals 1, we're done. And so I should have said this explicitly. So assume that f of 0 is not 0 and that f of 1 is not 1. So if f of 0 is not 0, then g of 0 can't be 0 either, right? Yeah, I should have said that a little bit more explicitly. That was just a little bit sloppy on my part. Okay, so now we're going to transition into EVT, and I'm really hoping I'm going to have enough time to get this. So same sort of thing. We're going to prove a little sort of mini lemma beforehand. There's a reason why the EVT is harder to prove, and it's because the thing that you need for the EVT to actually be true is a little bit more complicated than the thing you need for the IVT to be true. And again, it's kind of hard for me to explain exactly what that is without going into some topology. So if this is continuous, then it's bounded. All right. So every bounded function, every continuous function is bounded rather. And so last time, remember or not last time, but I guess maybe 2 weeks ago or so, we said if the limit exists, it means your function is locally bounded, right? And so if the function is continuous, it means its limit exists along every point of AB. And basically that guarantees that you're locally bounded at every point. Now, unfortunately, being locally bounded at every point actually turns out not to necessarily be enough to guarantee that it is bounded. For our purposes, it will be, but generally it doesn't have to. But that's basically the idea, right? So we're going to do the proof in the exact same way. I'm going to say, like, let's take now let's take intervals on which my function is bounded. It's going to be non-empty, bounded from above, so its supremum exists, and then that supremum has to be the entire, or has to be, the endpoint of whatever. I'll write it down. So define. This one's a little bit close, I think, to uniform continuity. So define B to be the collection of. Do I want to use X? I think it's okay to use X. Hopefully, I don't. Okay, so that f is bounded on the interval AX. Okay, again, so we're going to do our usual thing. We're going to say this is non-empty and it's bounded from above by little b, right? So note that A is in B, so B is not empty, right? Because the function is continuous at A, so therefore it's locally bounded. Maybe I should say that. note that F is continuous at A. And so locally, right? Because if I'm locally bounded at that single point, at the point A, that's enough, right? Because that means I'm bounded at A. I'm bounded on the interval A to A, right? So A is in the B. And B is bounded from above. Big B is bounded from above by little b. By the completeness axiom, its supremum exists. What do I want to call it? Do I want to give it a special name? Let's call it S. Okay, is everyone okay there? I'm using this fact from way back in the day, and I'm going to use this more. Remember when we first started talking about limits, and I think it was maybe when we were doing limit laws, or maybe just before that. And I said, if the limit exists, then your function is locally bounded, right? And one of the things that we did in that lecture is I said, can we think of a function which isn't locally bounded? And Yvonne gave us an example of one, right? So it was that lecture, if you remember it. So we're going to use that a lot, right? We need that local boundedness property. So by the completeness axiom, the sup of S exists. So the claim S is equal to B. Because if we do that, we're done, right? Then that means that F is bounded on, is going to be bounded on the whole interval AB. Okay, so for the sake of contradiction, suppose S is strictly less than B. Okay, same sort of proof as in uniform continuity. Since little b is an upper bound, we know that the least upper bound is less than or equal to it, right? So the only thing we have to do is to suppose that S is strictly less than it, right? S can't be bigger than it because it's the least upper bound. So let's assume that it's strictly less than, right? Well, now I'm going to use the local boundedness again. I'm going to use this forcing argument. I'm going to say, look, my function is continuous at S, so it's locally bounded at S. And that's going to allow me to extend the interval on which I am actually bounded, right? So since F is continuous at S, it is locally bounded. At S, that is, there exists some m greater than 0. Let's say m and rho. For all x in S minus rho, S plus rho. Right? So this actually means now that F is bounded. If it, basically there isn't much argument here. I don't think I really want to say it. If you know that you're bounded up until S and that you're locally bounded also on an open neighborhood of S, then you're certainly locally bounded, or you're certainly bounded all the way up to S plus rho. And it's 2 lines to put that together. I don't necessarily want to write it down. Basically, take the maximum of the 2 bounds. But basically, so F is bounded on, let's say, A to S plus rho over 2. Contradicting the fact that S is an upper bound. Okay. So there is a little exercise here that you should try and prove on your own, which basically is if you're locally bounded up until the point S, and then you're locally bounded at S, that actually means that you're locally bounded on that slightly bigger interval. So I haven't proven that. I've kind of left that as something for you to do. So this actually shows now that that S is equal to B. S equals B. And then the last thing that you should do on your own, so just check this, it's like 2 lines, that in fact B is in capital B, right? And so we're done. Right, we just need that to ensure that it is actually the whole interval. It's not just that the supremum actually gives us, what am I trying to say here? The fact that the supremum is equal to B is nice and all, but it actually doesn't tell us that it's bounded all the way up to B, just that it's bounded on any interval, right before B, any closed interval up to, but not necessarily including B. So we just want to show that little b is in B in order to guarantee it. But it's the exact same sort of proof. You're continuous at little b, therefore you're locally bounded there. Therefore, you're done. Okay, and so proof of the EVT very, very quickly. And so like I said, I want you to give those exercises a check. And if you don't remember what they are, I will write them out for you so you can double check them. And then of course, I'm happy to help on Discord or Piazza or whatever if you're stuck. So the proof of the EVT, again, let's just go up. Let me show you what the EVT is so you remember what it is we're trying to prove. Oh, it's so far away. Okay, there it is. It's in the middle of the screen. So we're trying to show if you're a continuous function, then you actually achieve your maximum, right? And I said that a byproduct of this is that your function is bounded, but we actually already proved that. So that kind of holds independently of whether or not the EVT is true. But now we want to prove that the maximum and minimum are actually achieved, right? That there are these numbers, little m and capital M, which give me the maximum and minimum values. Okay, so that's just a little reminder there of what it is we're trying to prove. So the proof of the EVT is to say the following. So what we're going to do is look at the image. And in case you don't remember what the image is, it's this. Right? So since, or I should say, this is not empty. Since A is clearly in here and is bounded from both above and below, so both its sup and inf exist. Is that what I want to say? Yeah, okay. I don't want to actually call these, let's call these S's and little s because they're in the wrong place. Sorry, so I'm just going to name them differently. Okay, so by the completeness axiom. Okay, so I claim that there's some value which is equal to capital S. So there exists M in AB with f of M equal to S, right? So again, I know that because my function is bounded, its supremum exists, but is there actually a number which achieves the supremum, right? That's what we're actually trying to prove here. That's the important thing. And the proof is going to be the same for the infimum, so I'm not going to do that one, but here's the proof for the supremum. So the proof is, for the sake of contradiction, assume not. Suppose not. We're going to define this function. That should be an arrow by g of x equals 1 over m minus f of x, which is continuous. Right? It's continuous precisely because its denominator is never 0. we've assumed there's no value of f which actually achieves the m. And so, this function is now continuous because it's not, denominator is never 0. But because this is a continuous function, it is also bounded. Right? So to arrive at a contradiction, I'm going to show this function is not bounded. So let's say, what do I want here? N to be, yeah, so let's greater than 0 be such that, oh, the clock is running out. G of x is less than or equal to n for all x in AB. Okay, and then I'm going to say let epsilon be less than 1 over n and choose what I want, x naught in AB such that m minus epsilon is less than f of x naught is less than or equal to m, right? Because m is the supremum, I can do that. But then, okay, so m minus f of x naught is then greater than epsilon. Is that m minus f of x naught? Here, let's do it more carefully. So f of x naught minus m like that. If I put in the negative sign, I'm going to get 0 is less than or equal to m minus f of x naught, which is less than epsilon. And then if I take 1 over, it also flips it. So I'm going to get 1 over m minus f of x naught is greater than 1 over epsilon. But here, right, so that should be greater than n, and that's a contradiction. The fact that g of x is less than n, right? And so we're done. What is one? It's a function, right? It's this function. So when you plug an x into that, you can actually evaluate what that function is. But because if we assume, well, because the entire point is I want this function to be continuous. And it is continuous as long as there's no value which makes that denominator 0, right? Because f is continuous, so m minus f is continuous. And we know that when you divide by continuous functions, it will be continuous anywhere where the denominator is not 0. I'm trying to show that there is a value which makes this function, there is a value of f of x, which is equal to capital M. And by defining this function, I can clearly get f of x as close to m as I want, right? That's the idea. I can make f of x as close to m as I want, which means I can make the denominator as close to 0. So g of x is going to shoot off to infinity, right? It's going to go off and it's as big as you want it to be. But that's not possible because we just proved that if you're a continuous function on a closed and bounded interval, then you're bounded, right? That was the proposition that we proved up here, right? So if you're a continuous function on a closed and bounded interval, then you're continuous. Well, this function g of x has to be bounded, but it's also clearly unbounded because f of x can get as close to m as it wants. That's a contradiction. Therefore, there has to actually be a value such that f of x is equal to m, and we're finished. Could we have taken another function? Certainly. Yeah. I mean, just the point is that you want it to be continuous and unbounded to arrive at this contradiction. I didn't do the proof here for this little s, right, which is the minimum. So try doing it for little s as well, but it's the same sort of thing, right? It's just you can get arbitrarily close to little s. So maybe take 1 over, f of x minus s. This function is actually always positive, this g of x that I defined, so I didn't even need the absolute values. But you're probably going to use something similar. If you wanted to use like m squared minus f of x squared, you could, right? Any of those functions would work as long as it's continuous but unbounded so that you arrive at a contradiction. Okay, so I had to fly through that a little bit quickly, but that's because this is technically term test material. but that's the idea there. Okay. Now there's not a lot of great applications. And of course, if you've got to run, and this is being recorded, there's not a lot of great applications for the extreme value theorem until we kind of get to them. Usually we use the EVT to do a lot of proofs, but it's so unlike the intermediate value theorem, which had some very nice immediate applications, EVT does have nice applications, but they tend to be more proofy anyway. We make a contradiction. So the assumption is that m minus f of x is never 0, right? For a contradiction, we're going to assume that number m minus f of x is never 0. And that gives us our contradiction, which means there's some value such that f of x minus m, or m minus f of x is equal to 0, right? Namely, f of x is equal to m. Yeah. Okay, everyone? So that takes care of it. Like I said, these proofs are pretty long, right? If you take like the proof of the extreme value theorem in its totality, it ends up being quite long. If you look at Spivak, I think the section in Spivak's book is actually called 3 Hard Theorems or something like this. And the theorems there are precisely IVT, EVT, and the uniform continuity result. These are pretty tough theorems, all things considered. They're not necessarily the hardest that we're going to do, but in some sense, they're the trickiest that we'll probably do. So just kind of keep that in mind, and don't let that get you down too much if it doesn't make sense. I show you these proofs because this is being 157, you should see them all. The reality is that this sort of proof technique is not going to come up again, right? This where we define B like we did at the top of the screen here, and then say, oh look, it's not empty and bounded from above, and you take its supremum, and then you argue that its supremum does something. That's not going to come up a lot, so I wouldn't invest a lot of time trying to understand these proofs. The proofs have a nice idea to them. There's something cool about that, but like I said, it's not worth losing a lot of sleep over if you don't understand them. Okay, it's not going to come up a lot, so invest a little bit of time, but not a crazy amount of time, right? Well, I mean, give it a shot, right? Like think about it for a bit and spend like 5-10 minutes thinking about it and see if you can come up with it. But like I said, so invest a little bit of time, but don't invest a lot of time, right? It's not worth investing a crazy amount of time trying to understand these proofs because they never, again, these are the sorts of proofs that I usually have to look up a couple of details when I teach them, because I don't remember how they work, because these proofs never come up again, right? These proofs are much better proven topologically. And again, you don't necessarily know what that means, but there are much better proofs of these theorems that we just don't have the tools to access. So like if I prove these theorems for myself, when I have that mental image of what these theorems say and how their proofs work, I do the topological versions because those things are very intuitive. They make a lot of sense. They're very easy to prove. These proofs are what I consider to be an analytical adaptation of a topological proof, which is why they're hard theorems, right? They're actually easy theorems. It's just that we don't have the right tools. And so we end up kind of doctoring and smushing the topological tools into analytical tools. And so that's why they look so nasty. But like I said, even in higher year mathematics, if you go and you do a lot of mathematics, this isn't how these theorems are proved. So not worth investing a lot of time into understanding them. Just give it a little shot and see if you can make heads or tails of it. But like I said, don't worry about it too much. No, it's not even hard in R. It's just you need to know what the words connected mean, and you need to know what the word compact means, right? And the word compact, right? So for the extreme value theorem, the word that you want is compact. And the definition of compact is that every open cover has a finite subcover, right? So a set in R or Rn, or frankly in any space, is compact if and only if every open covering of that set admits a finite subcovering of that set. And this is, those words probably freaked you out. You're like, what the hell is an open cover? What is a finite subcover? But if you know those things, then this proof is trivial, right? Like there's almost nothing to prove that the image of a compact set is compact. And I mean, you want to prove Heine-Borel then, you want to prove that the compact sets of R are precisely the closed and bounded sets. There's a couple of things to prove, but they're all relatively simple. And that gives you the result, right? And that's really not hard. The extreme value theorem is the statement that the image of a compact set is compact. It's practically a trivial proof. It's so easy. So Like I said, don't worry about these too much. Okay, a little bit. Worry about them a little bit. On a term test, maybe I could ask you something about these proofs, but you have them in front of you, right? You could go into Spivak, you could go into my book, and you have those proofs accessible to you. So, I could ask you to prove, for example, maybe one of the exercises that I said, hey, make sure you can do this, right? That seems like something I would do. Right. Yeah, actually, believe it or not, in that case, I actually think the extreme value theorem is harder to prove from a purely topological viewpoint. Because proving that the intervals A, B are precisely the connected intervals. So to prove the version topological thing you need for the intermediate value theorem is connectedness. And the definition of being disconnected is that you can't be written as a disjoint union of relatively open sets, and then you're connected if you're not disconnected. And proving that the intervals A, B are precisely the connected sets of R, that one's actually a harder proof than proving that the compact sets are precisely the closed and bounded sets. So it's weird in that sense that the topological proof actually is easier analytically and harder topologically. And then the extreme value theorem is easier topologically and harder analytically. So there's some sort of conservation of work thing going on there. Okay, anyway, we've run quite late because I've been blathering on. If those things sound interesting to you, they're talked about in 257, regardless of which campus you take it at. Though at this campus at UTM, I do that in a much more generality. We do that in arbitrary metric spaces. At St. George, they only do it on Rn because they're plebes. And so if you want to learn the cool version of this, you can take it here at UTM with me. If you want to do the plebe version, go do it at St. George. And you can tell them that I said that. I have no problem with that. But that's kind of your core, whatever. You're not even worried about 257 at this point, right? It's just surviving 157. So that's going to call it a day. Tomorrow I will post information about the test because the test is next Friday. So I'll post more information about that probably tomorrow. So keep an eye out for an announcement. But basically, it's everything up to and including now, right? And you imagine I'm not going to cover the stuff that was on term test 1 very extensively, but you still need to know things like, what does injective mean, right? Like you still need to know what that is. So it'll basically be all the limit stuff, right? That we've covered up to and including now. Exactly. What is injective? Okay. And in fact, I promise you, one of the words injective, surjective, or bijective will show up in the term test. So I promise you, you need to know what those words mean because at least one of them will show up. Do you need 247 for 257? No, at UTM in practice, I'd let you in with 223. You have to have some linear algebra, but like sup and inf. We even just used it, right? So I think it would be fair to say like, yeah, you should know how sups and infs work. In fact, yes, I can guarantee you that sup and inf will show up. Yeah, for sure. See you later. You too. See you later. All right, everyone, I'm going to take off. Yeah, but have a great weekend. I will see you bright and early Tuesday, unless I see you Monday, I guess. Bye, everyone.